There we go. So first of all, apologize for the delay in getting the video up for pseudo recorded lesson of what we did in class on Tuesday in a low-tech fashion, and hope I'm not missing any pieces and parts of my computer in the future. But in any case, the lectures usually will just be up here. It takes a little while for them to process, so sometime around 4 p.m. they should be up there. Your homework. You do have more iMath.AS homework. It's kind of scattered every 3, 4, 5 days or so. Some of them are closer together than others. But all the material on them is stuff that we've talked about so far. These first several assignments, well, one was extra credit, one was about how to use iMath.AS. But I hope that you finished assignment number 2, which was about small changes and constant rate of change. And I know there was a question about the tortoise and the hare, a variety of questions, and they're in question types. Some of these should probably seem familiar from earlier classes. Some of them might be new notation or vocabulary for things that you talked about before. But like I said, a lot of the beginning of this is just making sure we're all on the same page so that when we discuss things with one another or when I'm talking in lecture and you're just listening, that you know what I'm talking about. Now, please do ask if you don't know what I mean. If something's unclear, or whether it's because you don't know the word or because I was too vague, because I make mistakes and hurry through things sometimes, skip a couple words that are kind of important to understand, make sure you ask. But what I want to do today is, instead of learning a bunch of new things, what I want to do is practice a few things, one of which is just, in general, practice a little bit with GC. GC we're going to use in a variety of ways, a lot in recitation, and I'll use it for demonstrations in here. We'll do some activities in here as well. But for today, a lot of it, we're going to use a little bit of function notation and some other things. But some of the questions will be similar to the things that you're going to be asked to do for recitation. You should have all had recitation by now. If you added late and missed your recitation, like if you added in on Monday or Tuesday and your recitation was Monday, make sure you look for your assignment. There is an assignment. It's listed. Let's see, where is it? Recitation documents. Sorry, this is my teacher view. I've got a lot of stuff on here. But recitation activity 1, you'll see it's due September 4th. This is submit online. So there's a place to upload a file, and it's a file that you're creating in GC. So I want to make sure you know how to use this program. If you did miss your recitation, there are lots of office hours. Office hours, other than the general math tutors that are tutors for 270, these are all up now. Let's see. Oh, there it is. So you probably can't quite see that from here, but you can on your own personal device. So you're welcome to go to any of these office hours. My hours are Monday and Wednesdays in the morning. Most of us all have hours in the morning because we all have recitations and lectures in the afternoons. The tutor center will have tutors designated for 270 aside from the TAs and lecturers for this class. They'll have a lot of them in the afternoon and evening. We just don't have those hours back from the tutor center yet as to when all of our people are going to be there. But if you wander in, there's somebody that can help you. It's just they don't have the whole schedule together. They are just finishing up hiring everybody. So in any case, then make sure you come to office hours and ask if you missed your first recitation, especially if you're a Monday person, because the due date for that assignment is before you'll have your next recitation. Next Monday is a holiday. Labor Day, there are no classes, including no recitations on Monday. So don't come to campus expecting to find office hours. There won't be any. Tutor center's closed. All the campus offices are closed on Mondays. But back to main page here. Yes? No, you do have recitation on Wednesday, but so how it started out is Monday started out being ahead of Wednesday, and then after this Wednesday is going to be ahead of Monday. But there will be a Wednesday canceled, like right like the day of the test, or something, because kind of a recitation while you're testing, or I think it's actually the day after. It's right around the test. It doesn't make sense to have a recitation that day anyway. So then we'll be all equal again and start over after that. But let's see. Oh, so I want to go over these a little bit. The car and sink, which that's the piece of paper, the two-sided piece of paper I handed out on Tuesday. We'll go through that, but I do want to do the GC first, just for a little bit of practice at that. Now, you can open it up through here. It's just a PDF. This isn't a GC document. but I'm just going to pull up GC so that I'm not going to flip back and forth. If you want to read what the instructions are, you can flip back and forth on your device, but I don't want to make everybody dizzy in here flipping back and forth between two programs repeatedly. So let me just get my GC going, and I'll get this out of the way. If you open up that sunflower document, I'll just show it quickly here. It says the height of a sunflower is modeled by the function h of t equals negative 0.1 t cubed plus 1.7 t squared minus 0.6 t, where h of t is the height of a sunflower in centimeters at t days after the seed germinates. The function is only valid up to 10 days after germination, or in other words, our domain is 0 through 10. So we're going to play around with this, take a look at a couple of aspects of this graph, but mainly I just wanted to talk about the keystrokes and menu items that will allow you to do some fairly common graphing items in GC. And so you might have talked about this a bit in recitation, maybe you didn't, it depends on how fast you went through some of your other details in class. But the one thing I did want to talk about says define the function h in GC using x as the placeholder for the independent time variable. So there are a few letters that if you try to type them, it'll either give you errors or start doing unexpected things. For instance, if you type E, you can't use E as a variable because whenever you type E, it knows it as Euler's constant 2.718, etc. T is specifically reserved for GC doing graphs using parametric form. So if you start typing T, it's going to expect a pair of equations and it'll get confused if you don't have input like that. So avoid using T if you're trying to do this. So if you have lots of time variable equations, use T just because T for time is easy to remember. You can use any other letter you want, including X's and Y's, although not usually recommended because it can be a little bit confusing to look at. But if I want to use x as the placeholder for the independent variable, I can use absolutely anything I want. But to define a function, all you have to do, and I think we talked about this actually on the very first day of class, is type in the function rule. So from that point on, GC understands what you mean, just like as if we're having a conversation. Suppose h of x is given by this formula. I can write it just like on the piece of paper, except for I can't use t because of the intricacies of this program. But other than that, if you saw this in a math book, so it's not like a secret programming language, but if you saw this, like, oh, well, that's the definition of function h. The output is determined by doing this set of computations, including linear, quadratic, and cubic terms with x. Great. Now, it doesn't show a graph immediately. Now, mine does because I was doing some stuff with this earlier, trying to get my window in a visible size on this display. But the next question on here, past that part A, so part B, have GC graph function h on the interval 0 through 10. So this just defines the function. It doesn't say to graph it. Anyone know what you need to type into GC? You talked about this to get it to graph on the x and y axes? Yeah. Yeah, y equals h of x. Now, if I'd written h of a equals, and I had a's in that, if I want it to graph, I still have to write y equals h of x. For GC to understand that you're graphing, it wants the variables to be on the Cartesian plane. It wants it to be x's and y's. It's not going to change and say, let's suppose this is t and this is p. So it always uses x and y, just the generic, standard, independent and dependent variable letters used in every math book. So if I want it to graph, I have to tell it that. So what I'm doing by showing that is telling it, I want to see the y variables and x variables values, how they correspond to one another. Once you type this, to get a new line, you hit the, if you're on a Mac, it's a command button and then return. If it's on a PC, it's the control return. Or if you don't want to try to remember those until you get used to them, if you go up here, there's lots of different things you can do that are in these menus, and it'll tell you what you need to type to get certain new lines, etc. Let's see, where is this one? Oh, I'm probably not in this, so it's not going to show me. But if you need a text line, for instance, new text block, you can just click on that instead of trying to remember like what combination of keys, because that's when I always forget. It's on one of these buttons in a return, and it'll be a line where I can just type text instead of a line with a square next to it, which means it's going to graph something. So if I type y equals h of x, I can graph it, but I actually don't want all of this. What do I want? Just 0 to 10, according to the instructions. So all you have to do is just like it shows in there, and you can use less thans or less than or equal to's. It looks the same. But you'll have a comma, and then you can insert your domain statement. So this, again, it just make it look like what you'd see in a math book someplace. So 0 through 10 is what I want. We can't use interval notation. We'll just use the less than or equal to in the middle of a statement like this. But if you want to have like less than or equal to as opposed to less than to make it more match exactly, I forget what it is, like maybe control and then the less than. Yeah, on a Mac it's control. I think it's the same on a Windows machine. You'll see on Canvas there's a whole list of like keyboard shortcuts. You can just try pushing a button and taking a guess and see what happens. It's always a fun way to play around with computer programs. I wonder what's going to happen if I push these two buttons. Yeah. Oh, control and then, so the less than, so shift and the less than sign. So on a Mac and on a PC, I think it's control also. I don't have one to play with right now. But then I want X to go from 0 to 10. Now, if I just use plain less thans instead of less than or equal to, it'll look exactly the same. It doesn't like put big dots at the end or anything like that. And so if I hit graph again, it should show this. Now, one thing I wanted to point out about your graph, yours might not look like this. You can drag around your graph and change the scale of the axes and zoom in and out. There's a lot of different graph adjustment features. One thing you can always do, where it says graph, you can set this 2D range. It's not exact. It's not like on a graphing calculator you say go -10 to 10 and it chops it off there. The numbers that you put in there will be visible, but they're not going to be the edges of the screen. But a couple of things you can do on this. You can, first of all, you can drag this around. So if your graph is way over here and you're like, oh, I need to see more of this. I'd like to see 0 through 10. You can drag where the center of the axes are, where the origin is. And that's just grab onto the axes and pull. Either axis will work. If you're zoomed in or out too far, get this out of the way for a second, these two little mountain things down there are zoom buttons. So this, just in general, I can zoom in and zoom out. But you can also, instead of just generally zooming in and out and zooming out, you could do a couple of things. You could zoom in one direction only. And to do that, it's those little buttons down in the bottom left corner of the keyboard, and it varies between Macs and Windows machines. But on Macs, it's options and command buttons. So if you can see, if you push these buttons, there's little arrows that appear by those mountains. So on mine, if I hit the option key, I see arrows in and arrows out. That means it's just zooming in the X direction. So I can hold that key down and then click one of those to zoom in or out just in one direction. And my other key gives me, that's the command key on a Mac, gives me arrows up and down so I can zoom in and out just vertically. So you can control and do zooming that way. Also, let me just zoom out a ways. If I had it really tiny, I'm like, oh, I just want to see that. I don't want to try to zoom out and get it just right. Another thing you can do is a shift click. I think I showed this before, but if I hold down the shift key and then draw a square by just clicking on the graph, I can zoom into that region of the graph and then just let go. And so you can adjust to your liking. But I'm going to zoom this out a little bit vertically. I guess zoom in, that would be. So see if you can get your graph to look relatively similar to this. I put a lot of instructions on there, but just so you can see this, you can see the whole curve from 0 to 10. It's not squished into a little tiny bit on the left edge of the screen. So play around with the zoom features and see if you can do this, because we're going to draw some additional items on here. And we're going to utilize function notation as well as just the point plotting, which is a little bit strange looking. Question? You can change either one. So you have a Mac, so if you hit the command button, that does the Y up and down. If you hit those zoom mountain pictures, if you use the option button just to the left of that, it'll make horizontal arrows, and so you can zoom in or zoom out just horizontally, just in the X direction. So you can kind of customize graphs to what you want to look at the time. It's just, instead of having to type in numbers to view a particular window, you can zoom in, zoom out in one direction, two directions, or shift and click, like visually choose what you want to zoom in on. All right, so that was steps A and B. And then C is just kind of make it look somewhat similar to this. So you can see the whole graph. It's relatively spread out across your screen. Oh, and by the way, if you didn't notice this, if your graph area is too small, this little dot in the center here, you can drag and click that to have more or less formula area showing. Although this, you can scroll through this once you get more of it. So you don't have to have all of it showing. You can make it be hidden. But what I want now is, first of all, one other thing I want to point out, you can change the color of your graph. Like, I can make it black. Just click on the little square and pick your favorite color. Only some colors on this screen are going to be pretty visible to you. Green and yellow don't show up very well from a distance, but let's leave this as blue since it's that color now. So step D says to have GC plot a dot on the function to highlight the exact correspondence point, so an XY pair, where the independent variable has a value of 4.245 days. So what I don't want you to do is to try to figure out what the Y value is by plugging in numbers, because you're using a computer program already that knows what this function is. But two things we need to do. One, we need a new command line, a new line to type some math stuff to do, because it's not a continuation of the same graph. And if you do that, it does make your graph go away, but you can, if I wanted to see it again, let's graph this again. There it is. But I want to go back to here. Now it's got a question mark because I hit graph while I had nothing typed. But what I'd like to plot is a coordinate pair, and where you can find that on here, 2 vector. Now, so if you've taken physics classes, you might have used vectors to describe two-dimensional motion. But this uses it also just to describe a starting point. So if I select this, I can just have this 2 lines, and it shows x, y. Now this is not, I said 2 lines, 2 entries. There's 2 lines in this matrix is what I've got. So x and y, if I plug in numbers that I want, it would plot that point. So if I put in 2 for x and 7 for y, it would plot the point 2, 7. Now, do I want that point? No. I was supposed to be plotting a specific point on the graph where the independent variable, the number of days, was 4.245. So 4.245. And I want it to be on the graph. I don't want it to be at height 7. How would I describe, or how can I represent, without having to calculate it myself, the height of the sunflower after 4.245 days? Yeah.
You could just put in h of 4.245.
Yep. Oh, and make sure, so I define this with a capital H. If you use a lowercase h, you have to keep using the same letters. It doesn't know that lowercase and uppercase are kind of the same if you're writing sentences. It's a math book, so capital H is different. And I want h of, exactly, 4.245. So now it's right on the graph. I didn't have to calculate it myself, which is good. This is supposed to be a smart program. It knows what function h is, so when I put in h of 4.245, it does the computations. If I want to see what that height is, besides like it looks a little bit more than 20, I can click on the graph. And I don't have it exactly at 4.245, but I just clicked on it. I can drag this around and try to get it to be, nope, I'd have to zoom in farther to be able to drag it on there. But you can see by clicking on the graph that you have drawn, you can trace along and have it stick to the graph. It's just you're not going to get every x value necessarily. If you go in closer, you can go through a wider variety of them to be able to stop more precisely where you want. But back to this. So there's this spot. Now what I'd like to do actually is, let me drag this down here. is have GC draw lines kind of like that. Only instead of going up from the x-axis and going all the way up and across, all the way across, and just kind of close to that point, I just like to have a line going up from the x-axis and over from the y-axis, kind of saying up from here, over from there, so you can read the values. So if I want to have this draw a vertical line, you know what equations of vertical lines look like. I just have to tell it what vertical line I want. So the equation of that particular vertical line would be what? Yeah. Yep. X equals 4.245. Now, if I'm going to change the color so it's visible. There we go. If I just write that, I've got the full line. What if I just want the line segment that goes from the x-axis up to the curve, up to where that red dot is? What could I append onto this line here? Yeah, y is less than or equal to, let's see, y is between, we'll say it in English kind of, between what and what? Yeah, 0 and h of 4.245. Instead of saying 0 and 20 or 0 and calculating the number out, I can just write, oh, well, I want y to be between, and I'm just going to do the simpler type less than, y between 0 and h of 4.245. And you can check and say, oh, yay, that did it. That made a line segment that only goes as high as that red dot. Now what if I want the horizontal line segment that goes between that dot and the y-axis? Similar sort of expression, right? Mm-hmm. Yeah, yeah, so that 1y height is that dependent variable value at the spot, so y equals h of 4.245. I'm going to change this from green again. But I only want the piece of it between the y-axis and that dot, so that's restricting x or y? Yeah, restricting x just to be 0 through 4.245, right. So, comma, and then 0 to 4.245 as my values of x. Now, here's the trickier part. Now, one of the cool things that GC can do is that it allows you, and I'll do this a lot in class just as demonstrations, we can have motion demonstrated on here by using what GC calls a slider. What this is, it's kind of like using a parameter and then letting that parameter take on one value, change it to another, or you could even play it and see what happens at a whole variety of values, make it act like a variable. So the one thing that's pretty specific in this is we used one specific point when x was 4.245. So if I wanted to repeat this whole process but have it take place at x equals 6.128, or whatever number, every place up here, I'll just scoot this down a little bit, where I have currently 4.245, if I changed it to a different number, I would have the same graph, but going through a different point. So if I change this, I'll just type something easy. If I change this to 6, every time I see 4.245, if I change it to 6, it should be the same sort of thing, but going through a different point. Right? It's going to go through 6 comma h of 6. So if I want to be able to do that just in general, n is a letter that's built into GC for use with automatic, like internally built in what they call sliders. So if I go back and instead of 4.245 or 6, I just change this to n. As soon as I type n, you'll see there's this little bar at the bottom. Right now it says n is 4.3, but I can change that. I'm going to change all these 6's to n's. So I have x equals n, y goes from 0 to h of n, meaning any number I want, and I can look at one value at a time, like this. This is n equals 4.3, so close to that 4.245 we had before. I can make it bigger, though, and look at this for any value. And one of the things, and this has specific settings to this, if you click on the n, it tells you that using this built-in slider, it'll go from 0 to 10, going by in 100 steps, so counting by tenths, that is. You can change the letter if you want to, but if I want this to go from 0 to 14 in 1,200 steps, I can change that if I want to. Now, that'll probably go slowly. Oh, 500. All right, so 500 steps then. But there's more decimal places of accuracy on my N slider now. And there's a little play button here. I could even have this, I just changed it to go to 14, which is nonsense since this ends at 10. But I can look at what happens to the X and Y values as X increases. So N here is, in reality, for any pause value, you're just using it as a parameter placeholder. So what if this N is one thing? But if I let it vary, what this is doing is letting us visualize all the individual values of X. We talked about briefly like how people graph things is, you learned probably in like later elementary school, middle school, plot some, like plug in numbers for X, you get a Y, you get a few dots, and you try to guess what goes in between. Computers are really fast at computing, and you can imagine that this is the slow motion version of GC creating a graph. It's finding all these corresponding X and Y pairs and drawing them in a line. Now, how I could make this cooler would be, well, instead of having this go from 0 to 10 and showing the whole thing all the time, I could have it go from 0 to N, and that way it'll only show up to where this dot is. So I can imagine this, and this is how I have some of my animation set to like, so it looks like it's generating a graph. You can see in slow motion what the computer is doing in order to generate a graph, finding all these corresponding X and Y pairs according to this formula, calculating out infinitely many things. Well, it's not really infinitely many. Apparently it's 500. But that's a lot more than you would do on your own. But we were talking about constant rate of change, and this is not a constant rate of change sort of linear function here. It's not a linear relationship between X and Y overall, between 0 and wherever. But looking at just this center portion right here, that looks pretty darn straight to me. That looks like a straight-ish line. So if I were talking about estimating rate of change, if I look at small portions at a time, I could even look at a relatively large portion here and say, oh, well, that looks like it's going up at a rate of, find some precise points and pick Y's to X ratios, find those, estimate that constant rate of change. If I were to look back here, it looks right here less like a straight line, but if I were to zoom in, I can make that area look more like a straight line. I guess that looks relatively straight there for like 1/10 of a unit if I zoom in close enough. And this is the premise behind a lot of what we're doing, is that if you have a relatively, what looks like from a distance just a smooth function, if you zoom in close enough, it's going to look linear or linear-ish. So we can use approximate constant rates of change to describe what's going on in the function. We can talk about a function's rate of change in various different moments, and it'll change from moment to moment, from X value to X value, if I don't actually have an overall exactly linear function. But that's how we can talk about these rates that differ from place to place by finding a way to say, well, it's approximately linear or approximate constant rate of change between X and Y over small intervals. But in any case, just a little bit of GC stuff. I hope that maybe that's a little bit helpful in terms of your recitation assignment that you have to do. That recitation assignment, again, by the way, is in GC. You won't see quite as many things as I've got here, but this recitation activity 1, if you click on it, you don't get the options to edit it, but there's things to download and print, and then let's see, complete the activity and answer the questions in this quiz. So once you've done the activity that involves some questions that are kind of similar to that, make it do this, have it plot that, you're going to enter some answers that are in a quiz here. So this is the teacher view of it. It doesn't look like a quiz from here. You'll see it a little bit more neatly. But if I pull up the student view, there's all this bright pink stuff. It's a little distracting. All right, so the other thing that I want to talk about today, besides the sunflower, is cars and sinks. So sounds kind of weird, but Let's see. And this is also available in Canvas for you to download. Let me zoom in a little bit here. I don't know if this is going to be too big. That's too big. I don't want to see this side. Toolbar, no, whatever, close. All right, so talking about functions, and we talked about functions just in general in terms of the notation and the meaning of the notation. The one other thing, and I mentioned this in the recording that I did after the fact, I don't know if we talked about it in class, if you've forgotten the meaning of what is versus what isn't a function relationship. Something that's a function relationship means that the dependent variable actually depends on the independent, meaning if I give you an independent value, so if I make a statement like h of 4.245, that has one specific value at most, could be undefined, but you can't have h of 4.245 supposedly meaning a value of the dependent variable and say, well, what's the value? Well, sometimes it's 3 and sometimes it's 8. That's not a very useful sort of statement. So functions, things that are defined where one variable is a function of the other, the dependent variable is only one value of the dependent variable for any one independent variable value. So in any case, the phrase d is a function of t means that the value of d is uniquely determined, another way to say that, sort of fancy phrase, by the value of t. So uniquely determined means if I pick a t, there's only at most one d value that I get from this. So d is the distance in feet traveled by the car since it first started moving in this situation, and t is the elapsed time in seconds since the race car first started moving. So talking about this d is a function of t, in that statement, which is the dependent variable and which is the independent variable? So let's say which is the, if I can get this to pop up here. I'll restart it then. There we go. What's the independent variable in that statement? D or T? T, right. T determines D. D is a function of, or D is determined by T. So D is a function of T. So in terms of letters here, get this to right. See if it's going to be a good size today. The independent value, or the independent variable is T. So it actually asks which quantity. So T is the variable for this. So this is time. That's the independent quantity. It's measured in seconds, and its variable symbol is T. The quantity that's dependent, oh, it's variable D, is the dependent variable. So this would be our distance, which we measure in feet, and we assign the symbol capital D to it. Now, statement B says, using a function named W, so it doesn't have to be T or D, a function named W, write an expression for the distance traveled after any number of seconds T have elapsed. So D is the dependent variable, T is the independent variable, W is the name of the relationship between those two. And by the way, just to clarify here, W doesn't have to be a linear function or something with a constant rate of change for everywhere. Race cars generally don't drive one speed all the time. They try to drive as fast as possible, but when they first start moving, they're not going to be at top speed. So not thinking about constant rate of change, but just functions in general. If the function name is W, then W of T should be a way to express the dependent variable. So I could say that D equals W of T. So this is how those three symbols go together. This statement, D is the name of the dependent quantity. It's the symbol that we use for it. T is the symbol that we use for the independent quantity, and W is the name of the relationship between them. So D equals W of T. So if I want to use function notation to describe things, I'm not going to use D of T. It's W is the relationship. So W of something or W of T would explain dependent variable values or dependent variable just in general. So question 2 has a whole sequence of represent the following with function notation. So let me scoot this a little bit, maybe. Scoot. There we go. So we can see all of question 2 at the same time. So the distance traveled by the car after the first 9 seconds. And again, the notation that we're using, d is the distance. If I'm using function notation, though, the function name that we're using is w. So if I want to use function notation to represent the distance traveled by the car after the first 9 seconds, any thoughts or options on that? There's a couple different ways we could write that. Yeah. Yeah, W of 9. So W of 9, D was the distance traveled since the car started moving. So the first 9 seconds would be, well, 9 seconds after the car started moving. So our particular value of our distance would be given by this, W of 9. It's not D of 9. I don't have a way to compute a value for this, but this should tell me the distance that the car has traveled by 9 seconds after it started moving. So we'll talk about the second way you could write this, but let's talk about the part B first, and that'll kind of lead into that. The total change in distance, or the change in total distance, however you want to phrase that, traveled by the car between t equals 2 and t equals 5 seconds. Now, again, this isn't a constant rate of change, so I can't say, oh, it's like m times dx. I don't know what sort of function w is. Just using expressions with function notation, w of something. Any thoughts on how I can talk about how far the car traveled between those 2 points in time? Yeah. W of 5 minus W of 2. That sounds good. W of 5 represents but the distance it had traveled by 5 seconds after it started moving. If I compare that to where it was after only 2 seconds of moving, that difference in distances traveled should be the distance that it traveled during that time interval. So if this is helpful, if you want to think of during the time interval 2 through 5, I have a value of how far has it traveled altogether at both ends of that. No matter what this function looks like, if you want to think of this graphically, which you don't have to, we have no idea what this function might look like, but other than how it would have to go through the origin based on our definitions. After no seconds, it hasn't traveled anywhere since it started moving. It hasn't. But maybe it travels at a variety of speeds. But by time 2 and time 5 seconds, I'd have 2 different distances traveled. And if I want to know how far it traveled, I need to know how far vertically is that change. So these are values of D. I need to know how far D changed during that time. Now, going back to the previous question, I could make it a subtraction problem also. I just don't really need to because of the particular style of function that this is. But if I want to know how far it changed during the first 9 seconds, that's really talking about the interval like 0 through 9, right? How did the distance traveled change? I didn't compare 2 things that time because, well, distance started at 0. So whatever the value is by the time we get to 9, it's changed from where it was at 0 is just the value at 9 because the whole 0, 0 thing. So I could write this, the distance it's traveled by 0 seconds subtracted. So I can make it like it's not a different sort of question. It's just this is one particular sort of function where because of the way we defined our variables and symbols, W of 0 is 0. The distance it's traveled after 0 seconds is 0. So we just don't have to write this, but as an option. Now, if you haven't taken a look at these already, C and D, we can use the same sort of strategy to write these expressions. We're going to be writing expressions for general intervals, and both the independent and dependent variable change over those general intervals quite a bit in here. So an additional distance traveled by the car and the second 4-second time interval after it started to move. the second 4-second time interval after it started to move. What's the first 4-second time interval? Starting at 0 and going through 4. The next one, does it start at 4 or 5? 4, because we're continuous time all the way in between. So thinking about undo that. That was messy. Yeah, if I can draw a horizontal line. We'll pretend. So time 0 to time 4 is a 4-second time interval. The next time interval would go from 4 through 8, all those little fractional pieces in between. So I'm not talking about increments of time at time 0, time 1, time 2, time 3, time 4, thinking, oh, that's 5 seconds. No, from 0 up to 4 is 4 seconds, and then starting at 4 going onward, covering things like 4.1 and 4.7 and 5.3, all the decimal parts in between. The length of both of these intervals is 4 seconds, and we're talking about this one. So if I want to know how far the car traveled during that second 4-second interval, well, we can think of it similarly to this as long as you know what the interval is. It's the interval from 4 through 8, so W of 8 minus W of 4, right? All right. So part D, a more general interval, or a more weirdly described interval. The additional distance the car traveled over a 7-second time interval, beginning at a general time t equal to x. Ooh, there we go. So wherever this might be. So here's some general time, x. If it's a 7-second time interval, goes through someplace later, how would I describe the end of that interval? X plus 7. All right. So x through x plus 7 would be an interval of 7 seconds long that starts at a general unknown time x. So if I want to talk about change in the distance traveled, or that incremental extra distance traveled during that 7 seconds, I can say W of x plus 7, just following our same pattern, minus W of x. Now let me ask this. These are all subtraction problems. Looking at B, for instance, has a lot of numbers in it. W of 5 minus W of 2. Is that the same as W of 3? No. I mean, the value could come out the same, but it certainly doesn't mean the same. This W of 5, here, I'll just write down what I wrote. Is this the same as W of 3? Answer is no. But this is how far the car has traveled after 5 seconds. This is how far it's traveled after 2 seconds. This is how far it's traveled after 3 seconds. So those could happen to be the same number. Subtracting those first two equals the same number of miles as a third, but the symbols certainly don't mean the same thing. And they don't have to have the same value at all. They would have the same value if we had a constant rate of change all the time and we started at 0 like we did here. But that doesn't have to be the case at all. So just keep in mind with function notation, you can't subtract the inputs and expect that that's equivalent to having two subtracted outputs like this. So keep in mind the meanings of the expression. So similarly, this last one here, W of x plus 7 minus W of x, that is probably not equal to W of 7. It might happen to be the same number, but there's no reason that it has to be at all. So these sorts of expressions, we can't simplify them by subtracting the inputs just as a general rule. There's cases when they turn out to be the same number, but the meaning isn't the same. That would be a coincidence if they turn out to be the same number. So let's look at some pre-written expressions and see what we've got with those. Scoot this. Number 3. So thinking about the car and the distance traveled and times. So again, the definitions here, I'll just jot them down briefly to the side. The independent variable t was measured in seconds since the car started to move. W is the function that relates d and t. D is the distance traveled measured in meters. Meters that the car has traveled based on seconds that it's traveled. So these are just brief recap of what's up above since we can't see it at the same time. So those are just the units on those. W doesn't have units, it's a function relationship.
Excuse me, feet.
Oh, was it feet?
Yeah.
Oh, thank you. Thank you. That's less confusing. So D, distance measured in feet, since times 0, since the car started moving. T equals 0 is when the car started moving. So, breaking down what these expressions mean, because again, we're going to see lots of expressions, some more general than others, to try to overall define amounts of accumulation or rates and change for all sorts of situations. So this 2W of A, so W is a function name. A is in the spot where the independent variable would go. So this is talking about time after some time A measured in seconds. What about the 2 here? Yeah, it's doubling something. So assuming that these computations make any sort of sense, I'd be doubling the value of W of A. So W of A would be the distance the car traveled after A seconds. So this would be also then an expression for distance, but it's twice the distance, right? Twice the distance traveled, measured in feet. After A seconds. Now B and C should maybe look familiar, and D and E, they're all that subtraction of something. C looks a little weird. But B, if I wanted to talk about what this W of C minus W of 8 is, based on what we did up above, we had a series of subtracting 2 function values. Can you think of a way to describe what this subtraction could represent? Well, we can talk about, yeah.
The change in total distance traveled
Mhm.
by the car between t equals 8 seconds and t equals c seconds.
Right. So we're talking about the change in distance traveled over a specific interval of time. This one between t equals 8 and t equals c. So final minus initial. That's why it's from 8 to c, which was maybe easier to think about when we were the ones writing it. If you're reading someone else's written expression, thinking about these are 2 different values of distance traveled, for it to make sense as something we can interpret, it could mean this change in distance traveled, or the distance traveled during an interval 8 through c. So abbreviated distance traveled on the interval 8 through c, and that distance will be measured in feet. So give us a number of feet, how far the car traveled between time 8 and time c, or how far it traveled during the interval 8 through c. There's a lot of different ways you could talk about this. You could talk about the total change in distance from its starting point between time 8 and time c. Now, part C, W of 7.5 minus 9. If this is supposed to make any sort of sense whatsoever, let's see, W of 7.5 is a distance traveled. If this is going to make any sense whatsoever, 9 better also be something about feet and maybe distance traveled, although we don't know when it happened because it's not written in function notation. But this isn't 9 seconds. That wouldn't make sense as a, oh, take a distance and subtract time from it. So if this is going to make any sense, there's still a variety of things we could talk about, but this would also, this and the two below it also would all have to be, C through E would all have to be the same sort of thing. Talk about distance traveled during a specific interval. Although for part C, well, the distance traveled between, I don't know when this is, and times 7.5. Well, if it's a distance, I could talk about just this is 9 feet less than how far I traveled by times 7.5, since I don't know what time this 9 pertains to at all. But I can imagine that this 9, in order for this to make sense, would have to be something about feet. So I could say 9 feet less. Than the distance traveled by times 7.5. 7.5 seconds. Sorry, it's a little messy. So D and E kind of the same as B, with just more general input values, independent variable values. Points in time are a little bit more general. So let's just talk about the intervals. So we could describe both of these as how far the car traveled during certain intervals. What interval of time would this be? Starting at 3 and going through 3 plus h. So in terms of, I could word it kind of similarly to what we did for B and what we did with several of the questions from number 2. But the interval this distance is traveled during would pertain to 3 through 3 plus h, right? So if I wanted to, instead of saying the interval 3 through 3 plus h, sounding very math booky, if I wanted to say it slightly more Englishy, although it has an h in it, so it's not going to quite sound normal, I'm going to say, how long is this interval? This is an interval that starts at 3 and goes forward in time how far? H seconds, yeah. So it goes from, it's an interval of time that's h seconds long, starting at time 3. So if you wanted to have it, instead of 3 through 3 plus h, if you wanted to say that, you could rephrase it. Same sort of thing here, only this one has a general starting point. We could talk about the distance traveled during an interval t through t plus 10. So this one has a known length of interval. It's a 10-second interval starting at time t seconds, whereas the last one was an h-second interval starting at time 3. So each had one like real number and one kind of placeholder, one parameter used to describe a part of the interval. One was to describe its length, essentially, and the other was to describe its starting point. So again, B, C, D, and E could all be distances traveled during a certain interval, although C doesn't mention the time, so harder to describe quite that way. What about F? What could that be? Yeah. Huh? Okay, so this could be a rate of change. If you think about like slope computations, change in y over change in x. This is, the numerator looks kind of like the stuff we were just doing. It's the change in distance traveled during an interval x through x plus 0.5. Or in other words, the additional distance traveled during this particular half second, x, through a little bit, through half more than x. And then you can divide distances by lots of things. So this could have a variety of other meanings. Dividing by 0.5 is the same as multiplying by 2. You say, oh, it'd be twice that. So I could just talk about, oh, this means twice the distance traveled during that interval. And that would be perfectly valid. We don't have any context for why we're doing this. But looking at how it's dividing by 0.5, that's the incremental change in elapsed time. And change in distance over change in time, because the beginning and end of that interval that we're looking at in the numerator happens to be, the difference is the same as the value in the denominator. You say, oh, change in distance, change in time, that's like miles per hour, or feet per second in this case. But we've got this average rate of change. I don't know what this function W is, whether it's a constant rate of change function or something else. So we won't necessarily say this is the constant rate of change, but I can at least say it's an average rate of change. And this doesn't have to be the answer to this. This is just one way we could interpret this. The average rate of change in feet per second of the race car during this particular interval, an interval that starts at a general value x and goes forward 5.5 seconds. So an average rate of change over half a second, well, race cars can probably change their speed a bit over half a second, but in general, just you driving on the highway, your speed isn't going to change a lot in half of a second, probably, unless you're really trying to merge fast. In any case, though, this could be an average rate of change that's extremely close to there is a constant rate of change anyway, or maybe it's not very close to a constant rate of change over that interval, but that's one thing that this expression could represent. All right, so let me clear this off. Questions on any of this notation, functions, interpretations? There's a lot of room for variety in ways to interpret things, but just be careful. There are definitely things that could be incorrect, but there's a lot of ways to say correct things also. Yeah?
How do you know, like, since the very beginning that W means this?
Oh, so at the very top, let me scroll back up there. So D was the distance in feet traveled by the car, T was the time elapsed, and it said use a function named W to write an expression for, like, so the function W is what relates D and T. So W isn't distance, W is the relationship between time and distance. So if you say W of something, that's that dependent variable, or that's the distance component. All right, so on to the other side of this. So different scenario, we've also got a W, but capital H equals capital W of T. Let's say that this capital W is the function then that relates T, time in seconds, or no, time in minutes, sorry. And H is the height of the water in a semi-clogged sink measured in centimeters. So we were talking about sinks and sink clogs last class. We can turn this on and fill it up. If it's clogged, it'll drain, but it'll be slowly. So we're talking about the rate in centimeters per minute at which it drains. So the parts A and B of the same question, like 1A and 1B, are related to one another. What I want to do here is, this time we are using a constant rate of change. So this is kind of combining our function notation we were just working with in general with the concept we were talking about in class on Tuesday about constant rate of change. dy equals mdx, and y final is y initial plus, well, dy. So I believe, did I put those at the bottom of the page? Yeah, that's at the bottom of the page, those relationships. So this dy, since it's also mdx in a constant rate of change relationship, you can replace as y final as y initial plus mdx if you want. So keeping that in mind. Again, this we're talking about water's draining, so its height is decreasing at a constant rate of 1.23 centimeters per minute. What's 1.23 to this problem then in terms of common notation? Yeah, that's our rate, or the symbol that we had for that down below was m. All right, so I could talk about dy equals mdx. The symbols here aren't y and x, though. We've got h and t. So dh equals 1.23 dt. If I wanted to express values of h, I can use w of something. Again, w is just the name of the function. W of something gives me values of h, the height of the water. Now, get back to this. So if we want to, a computation and an expression using function notation for the change in the height of the water between time 2 and time 6 minutes. So since it's a constant rate of change relationship, we can actually do a computation for that. But just thinking about what we just did with the race car, what could I write using function notation that expresses the change in the height of the water in the sink over that time interval? W of 6 minus W of 2, good. W of 6 minus W of 2. Now, do I know what W of 6 is off the top of my head? No. Do I know W of 2? No. But if W is a constant rate of change relationship, then each of these are values of h. The change in the height, oops, I don't know why this is connecting. The change in a height is represented by this, and it should also be represented by mdx. Well, generic mdx, maybe mdt here. So this represents a change in the height of the water between time 2 and time 6, but since it's a constant rate of change, I can also compute that by knowing the rate and how much time has passed. So how much time has passed here? 4 seconds. dt here is 4, and my rate was 1.23. Now, do I want to calculate this? No, but I'll write out the computation. So we could calculate the value of this by doing 1.23 times 4, which is 4 point something, 4.92? 4.92 centimeters. Now, why I wanted to write this out? What's going on with the water in the sink? Is it filling up or is it emptying out? Yeah, it's draining. So what am I missing here? There's a negative. Yeah, that 1.23, that's the rate of change, but it's actually, it's decreasing. So if I want to be specific and indicate that, I'll use m as a negative number. So although you don't see a negative here, I know that it's decreasing at this rate of 1.23 centimeters per minute. So I can think of m being negative 1.23. And that's how I know that, oh, it's not the sink has 4.92 more centimeters of water in it, depth-wise. It's less by that. So however full it was after a 4-minute period, and it's because it's over any 4-minute period. It's a constant rate of change. Over any 4-minute period, the height of the water in the sink would drop by the same amount. So if I had W of 5 minus W of 1, it would be the same. Not in the previous question with the race cars, because who knows how fast they're going, but this says it's a constant rate of change. In a constant rate of change relationship, the change in the dependent variable value we can compute just from the change in the independent variable value, which is nice. So it's much less complex. This isn't true with functions in general, but this fact is nice about constant rate of change. And so if we can build from using constant rate of change to do more math, we can use this nice simple rule about converting from needing to know the y values to be able to express this with, oh, just the x values and the changes in those. Or whatever the variables may be. Here it's h and t. Now, all right, suppose that we knew that W of 2 was 8. Before I asked, do I know W of 6? Do I know W of 2? The answer was no. But if I know that W of 2 is 8, that's the height at the beginning of this previous scenario there. There were 8 centimeters of water in the sink at time 2. 8 centimeters deep at t equals 2. If I want to figure out a computation for W of 6, oh, well, I know what happened. That's 4 seconds later, and it's decreasing by 1.23 centimeters per minute. I can just use this previous expression, though, because this is looking for a computation for W of 6. This is the equivalent of y final. At the beginning of the interval, from part A, we had 8 centimeters of water. By the end, it should be this much less. As a computation, I could write function notation. I could write W of 6 equals, and be all fancy about it, but we already did some of the work above. W of 6 started at W of 2, and then it decreased by 1.23 centimeters per minute for the next 4 minutes. But I also know that this is 8 minus 4.92. So whatever that is, 3.08. And this is centimeters. So you can find this y final by doing y initial plus the change, which in this case happens to be a negative change. Yes? Oh, sorry, that was an at that kind of got swirly. So at t equals 2, that's what that was. Sorry about that, a little messy. All right, so what I'd like you to do, questions 2 and 3 are sort of similar, but with more general intervals to talk about. I'm going to leave this one up as a model for a couple minutes. I know you've possibly looked at this and already worked through it. Maybe the person next to you didn't. Maybe you both did. Compare notes and or ask one another questions. Take a couple minutes and see if you can figure out 2 A and B and 3 A and B. So one about an interval 4 through 4 plus K. And the other one more general than that. Yeah. We were given the initial value, W2 equals T.
Yeah, but like at times you.
Oh, yeah, so you could find this, yeah, you could find that if you wanted to. So, yes, once you have any individual point, we could find all of the others from it because of that concept. So if you go back and find, like, going up by 1.23 centimeters per minute for 2 minutes, yeah, absolutely. Oh, so the computation was like the 3.08 or like the minus 1.23 times 4. But so computation usually involves like more numbers or actually finding the result of the computation. Some of them have more symbols in them. So like W's, so we call it more of an expression. So W2 minus cosine 8 minus. All right, let's look at number 2. See if we're on the right track or we're figuring out how to kind of generalize our process a little bit. So for part A, same situation. We've still got W is the capital W is the function that relates time to height of the water in the sink, T to H, capital H. We want to write a computation and an expression using function notation. and you can do them in either order, both, neither, whatever, that represent the variation in the height of the water during an interval of k minutes starting at time 4. So from 4 through 4 plus k. So let's start with function notation. If I wanted to write something about the height of the water over this interval, think about what we did even with the race car when it wasn't constant rate of change. What expression with function notation would talk about the change in the height of the water, or how much that height varies, just using function notation? Yeah. Yeah, W of 4 plus K minus W of 4. So here's an expression with function notation that talks about how much the height changes during this particular 4-minute period. Now, because it's constant rate of change, it doesn't really matter which 4-minute period it is. It would be the same amount for any 4-minute period. So this uses function notation. If I wanted to just write out a computation, what would I have to compute to get an answer? Somebody else? Yeah. Yeah, so we get that from doing the 1.23 times 4. So MDT, oh, K, sorry, times K. 4 through 4 plus K. I was thinking K through K plus 4. Negative 1.23 times K. So this is our MDT. So to write an expression, or like what computation would you do? If we knew the value of K, for any value of K, we would do this. Negative 1.23 times K, since K is the length of the interval. Yeah.
Why is it K instead of 4 plus?
Oh, did I change it? No. Okay, so this goes from 4 through 4 plus K. How, if I go from 4 through 4 plus 7, it's 4 through 11, that would be 7 seconds. You get to subtract those. So this K here is representing this dt, the change in time, or the variation in time from the start to the end of the interval. If I think final minus initial, that result is here, K. So K is the number of seconds that elapse during that time interval. And so if there's 4 K seconds that go by, then the water would decrease by 1.23 times K, regardless of what K is. So for 2B, so let me just write this. And so you could think of it this way, but for any K second long interval, that's going to be K times negative 1.23, or negative 1.23K, would be the amount of decrease in the height of the water. The negative sign indicates the decrease. So if you had a value at the start of the interval, 5.7 is the height of the water at time 4, and I wanted to know after the next K minutes have passed, how high is the water afterward? Kind of same as before. I say, oh, well, y initial plus my change, mdx. Just this is general letters y's and x's instead of the ones from specifically this problem. But the beginning of the interval at time 4, the height was 5.7. And then afterwards, well, I'm going to write minus instead of plus, we went down by 1.23 centimeters per minute for K minutes. So this would be an expression for the height of the water K minutes later, which would be time 4 plus K, since the beginning is time 4. All right, I'll stop at that for today, since I believe it's the end of class. Yep. So just one last note. I'll talk about this on Tuesday, but a week from today, we're going to have our first written quiz in class. So just think about that. And I will see you many times before then.